But to do so, we must first think about inductance. First, a simple experiment. Here a coil is connected to an instrument for measuring current. We're going to push a magnet into the coil and watch the needle as we do so. There. There was a kick of current as the magnet went in, and there'll be another in the opposite direction as we pull it out again. There. Whenever the lines of force of the magnet cut across the turns of the coil, an EMF, an electromotive force, is induced in the coil, causing a current first one way and then the other. And this is true whenever the number of lines of force passing through a coil change for whatever reason. Now you'll remember that a current flowing in a conductor always produces a magnetic field. In the case of a straight wire, the lines of force encircle it. If the current increases, the magnetic field strength and the number of lines of force will also increase. If the current decreases, the number of lines of force will decrease. On first switching on, as the current builds up, so does the magnetic field. And on switching off again, the field collapses, taking time to do it. This also happens with a coil. We saw that when a current flows in a coil, it causes a magnetic field about the coil. On switching on, the lines of force take time to build up, and on switching off, they take time to collapse again. The results of these changes in the number of lines of force through the coil is that an additional EMF is induced within the coil itself. This is called an EMF of self-induction, or counter-EMF. An important feature of this EMF is that it will always try to stop the change happening. When you switch on, the induced EMF opposes the buildup of the field, slowing it down. And when you switch off, it tries to keep the field going. This is an example of Lenz's law. In general, Lenz's law says that as current increases in a coil, an EMF is induced which opposes the increase. And when the current decreases, the induced EMF tries to keep it going. This property of a coil to oppose change is called inductance. If a coil has many turns and a core of soft iron or other magnetic material, the induced EMF at switch-off may be very high, much higher than the original voltage. It can be so high that there's a spark across the air gap. The induced voltage is momentarily high enough to overcome the high resistance of the air in its effort to keep the current flowing. Such a coil with its core is called an inductor or choke, and is represented on circuit diagrams like this. If for any reason we want to avoid the inductance effect on a coil, we can double the winding back on itself so that the two induced EMFs cancel out each other. This is now called a non-inductive winding, and is shown on circuit diagrams like this. The unit of measurement for inductance is the Henry, and we often need to speak of a millihenry or a microhenry. And now we'll do another experiment. We'll take two inductors and space them apart in a square iron yoke like this. To the left-hand coil, we will connect a switch and battery. And to the other one, we'll connect a current measuring instrument. We now know that if the current changes in the first coil, as at switch-off, say, there would be a self-induced EMF in the coil opposing the change. Well, what do you think would happen in the other coil, if anything? Well, watch. A kick of current shows on the instrument. Every time the current changes in the first coil, there is an induced EMF in the second one. This is because the lines of force from the field of the first coil are cutting across the turns of the second one, so that as the field changes, an EMF is induced in the second coil. This is the EMF of mutual induction. It must have struck you that if, instead of switching on and off the current, we supply an alternating voltage to the first coil, so that its field changes continuously, we shall induce an alternating current in the other coil. And this is how a transformer is constructed. We call the first coil the primary coil and the other one the secondary coil. The alternating voltage applied to the primary coil is the input voltage, IP. And the alternating voltage produced in the secondary is output voltage, OP. But before we can understand how this arrangement actually transforms the voltage, we need to know something else about induced currents. Suppose we have 5 turns of wire in the primary coil and 10 times that, 50 turns in the secondary. And suppose we apply an input EMF of, say, 8 volts AC. The output EMF will be 10 times that, 80 volts AC. And we will have stepped up the voltage and we have a simple transformer. Let's look at it more carefully. The number of secondary turns divided by the number of primary turns equals 50 over 5 equals 10. But the output voltage divided by the input voltage also equals 10. Using obvious abbreviations, this means that the number of secondary turns divided by the number of primary turns equals output voltage divided by the input voltage. And if we do the simple bit of juggling, we get this formula. Secondary turns divided by primary turns times input voltage equals output voltage. All right, let's try another example. And this time we will use the symbol for a transformer used in circuit diagrams, 2 coils and a core. Let's take an input voltage of 240 volts AC, alternating in a primary of 100 turns. And let's take a secondary of 200 turns. What will the output voltage be? Well, the number of secondary turns divided by the number of primary turns times the input voltage equals the output voltage. So the output voltage is 480 volts AC, and we have again a step-up transformer. But you can also have a step-down transformer. Here's one. Secondary turns over primary turns times the input voltage. This simplifies to 5 times 8, that is 40 volts AC. The voltage has been stepped down from 160 volts AC to 40 volts AC. Transformers are constructed in 2 basic forms. This sort, where the coils are separately mounted on a square yoke. This is called a core type. The other type is the shell type, where the secondary coil is wound on top of the primary. Transformers, in fact, come in all shapes and sizes, but they all have one purpose: to step up or step down AC voltage. They don't produce electric power. They merely use the property of inductance to change the voltage. The next part will deal with another very useful property of electric circuits, which is called capacitance.